Okay, so in the last lecture, what we did was that we tried to apply the Ampere's law. We saw different examples for that. We tried to apply Ampere's law in order to find the values of magnetic field intensity H for toroidal coil as well as for a infinitely long current carrying conductor. After this, the next topic of our consideration is going to be the magnetic vector potential. As we have talked earlier about this, that for everything that was being studied in electrostatics, there will be a counterpart in magnetostatics. So we had electric potential, which was in uh, the last lecture, in the last chapter, sorry, in electrostatics, and as a counterpart of that thing, we have vector magnetic potential in this chapter. So the topic for today is going to be vector magnetic potential. So to ponder over the last electric scalar potential a little bit in order to compare these two things, we'll talk about that. That in the chapter 4 we studied what electric potential V or the voltage or potential difference actually was, and we studied that it is basically a line integral of electric field intensity along a closed path, and as a result we also studied a relationship between electric field intensity and electric potential that we figured out to be E is equals to minus nabla V. And the application of that electric potential was pretty simple, that it gave us another opportunity, it gave us another method to calculate the value of E if it is difficult for us to use the conventional methods like Coulomb's law, like Gauss's law. As an example of that, we studied an example in which we needed to calculate the value of electric field intensity for a dipole, and we clearly saw when we did that assignment that whenever we use the electric potential in order to calculate the value of electric field intensity, that was pretty simple as compared to when we tried to do that using the conventional methods, what you did in the assignment. This was pretty complex, but when you reflect back to the example that we did in which we used E is equals to minus nabla V, that was pretty simple as compared to that. So he says that the concept of electric potential basically proved itself useful in relating the electric field intensity with electric potential in the calculation of resistance, in the calculation of capacitance, as well as sometimes it was also used in order to find the value of electric potential E. So what the application was, it helped us to calculate the value of capacitance. We certainly used the value of electric potential or the equation of electric potential in order to calculate the value of capacitance. Similarly, we also use the value of electric potential V in order to calculate the value of R, the resistance, when we talked about or when we studied the resistance topic. So what he's saying is basically he's mentioning that in applications, the uses that in which the electric scalar potential was used. So he's basically stressing on the mm, importance of electric scalar potential in electrostatics, so that you may know that the vector potential or magnetic vector potential is also going to be of the same importance, or even if not the same, it is a little bit important because we need another method, we need another backup plan in order to calculate the value of magnetic fields, and we also will use this vector potential when we will talk about the inductance and self-inductance and mutual inductance and those types of phenomena. So the goal of today's lecture is to derive an expression for vector magnetic magnetic potential, just like we derived an expression for electric potential V. So how do denote the vector magnetic potential? Like we represented the electric scalar potential by V, will denote the vector magnetic potential by A, and it is going to be a vector as it is clearly mentioned in the topic of in the name of the topic, in the title of the topic. So we're gonna use a similar approach in order to calculate a vector magnetic potential for magnetic flux density, but there is a constraint. There was no constraint in case of electric scalar potential, but in vector potential, in vector magnetic potential, there is a constraint that we know according to Gauss's law that nebula B has to be zero at every cost. Why is it so? We have studied and the reasons behind this, because we know that the magnetic field is going to be in the form of closed loop always. So this means that whatever the expression we derive, it should satisfy this equation in order for it to work for the case of magnetic vector potential. So the goal is going to be to define B in terms of vector magnetic potential A with the constraint that the divergence of B should be zero always. So there was a property that we studied in chapter number 3. That property indicated that the divergence of curl of a vector will be zero. So we have this equation, we have this property, and we have this equation that we need to satisfy. And if we compare these two equations, if we call the first one 1 equation 1 and the second one equation 2, and if we compare these two equations, we can say that the B is equals to nebula cross A. This is the only expression which is going to satisfy the condition that we had to satisfy for magnetic flux density. This is the condition that I'm talking about. If the value of B is equals to the curl of A, then and the result will always, the divergence of that result will always be equals to zero. And this property is the one thing which is governing this principle. So he's saying that we can write the value of flux density in terms of vector magnetic potential by comparing these two equations and by deriving this equation. And he's saying that as this is an expression for magnetic flux density, then the value of, or the unit of this will always be Weber per meter square, or we can also call it Tesla. Okay, so if the value of if the unit of B is going to be Weber per meter square, then we know that the value, or that the unit of A is going to be Weber per meter. Sorry, Weber per meter. Now moving forward, he's saying that we know that by Ampere's law, we studied an expression that the curl of H, this is equals to the current density J, and this current density is basically due to the motion of free charges, due to the motion of free charges. If we want to express this equation in terms of magnetic flux density, why are we doing this? Because we can see that we are dealing with magnetic flux density from the start, from the scratch. So if we want to use this expression in some way in order to simplify, or in order to explain the equation for magnetic potential a little bit more, then we'll have to use the same terminologies that are being used in this expression, and that the terminologies that are being used in this expression is magnetic flux density. So if we want to mention this equation in the form of magnetic flux density, we know that B is equals to mu naught H. So what we'll do here is that we'll transform this equation in the form of magnetic flux density, and for that we have to multiply the right hand side with mu naught. So we have this equation. In this case, In order to keep things a little bit more generic, what he's doing is that he's not mentioning it as mu naught. In fact, he's mentioning it as mu. So this can be the permeability of a free space. This can be a permeability of a particular material. So if it is being used in a scenario in which the free space is being used, then we'll change this mu to mu naught. And if it is being used in some other kind of material, then we can put the value of permeability of that material into this equation. So in order to keep things a little bit more generic, he is using mu here. Now, referring back to chapter number 3, he again says that if we convert this equation in the form of vector magnetic potential, what we'll do is that we'll put the value of B in terms of A here. So what will happen? We'll have nebula cross, and what was the value of B? The value of B was once again nebula cross A. This is equals to mu J. We have this equation now. But this equation is still not a conventional equation. We'll need to simplify it a little bit more. We have to reach an expression. We have to drive an expression which is easy for us to calculate, like we did with electric scalar potential. So we need to simplify it a little bit more, because taking a curl of a vector and then again taking a curl is going to be a difficult task, because curl is a difficult phenomena to calculate. We have to convert it into a form of into a form in which we can easily take the integral, and we can apply it to different scenarios according to our requirement. So in order to simplify it a little bit more, he is referring to another property that we studied in chapter number 3. According to that property, nebula square of A was equals to nebula into nebula dot E, nebula dot A minus nebula cross A. So if we take a look at this property, we can see that we can simplify this expression by using this property a little bit. How can we do that? We can take this part of the equation to the left hand side, and we can take this part of the equation to the right hand side, and we will have the value of nebula cross A in terms of nebula square A and nebula into nebula dot A. Once again, it is not as simple or as simplified as we want it to be, but still we will get something to work with, and we will try to simplify that thing a little bit more. So what he is doing here is he is basically putting the value of nebula cross A by using this equation. If we do that, we'll write nebula cross A is equals to, we'll take this thing on the left hand side and this thing to the right hand side, and we can say that nebula into nebula dot A minus nebula square A. So he's going to put this value of nebula cross A into this equation, and we'll write this as nebula into nebula dot A minus nebula square A mu naught G. The problem with this equation now is that we have an expression in which there is a divergence of A. Now reflecting back to this condition that we needed to justify, this condition is the thing that we cannot compromise on. This means that for this equation to work, the divergence of magnetic field intensity has to be zero at every cost. He is saying that in order to achieve this goal, what should we do? What should we do to A that we are confident enough that there won't be any case in which the divergence of B will come out to be some value. We know that if that happens, the whole calculation that we did, it will demolish itself. Okay, so it will implode. So he's saying that the simplest way to ensure that the divergence of B always comes out to be zero is to take this assumption that the divergence of A is also 0. If we take this assumption that the divergence of A is always 0, then we can guarantee that the divergence of B will also be 0, because uh, basically this A is yeah, has been derived from this equation. So what he's doing here is that he's assuming that the divergence of A has to be 0 at every cost, so that the divergence of B should always be 0. So this will reduce this equation further, and we'll have minus nebula square A is equals to mu J. And if we uh, move this minus sign to the next side, we can say that nebula square A is equals to mu naught J. Now we have a pretty simple equation for vector magnetic potential, but still it is not in the form that we want. So what he's saying is that he's breaking it down to its x, y, and z components if we are in fact dealing with the rectangular coordinate systems. So he's saying that we can write this nebula square A as x hat nebula square ax plus y hat nebula square ay plus z hat nebula square az. So he's saying that we can write this equation into its different parts. How can we do that? We can say that nebula square ax is going to be equals to minus mu naught jx, the x part of the current density. Similarly, nebula square ay is going to be equal to uh, sorry, minus mu jy, and similarly nebula square az will be equals to minus mu jz. So what he's done here is that he is divided this equation into its three rectangular components form. Now once again, going back to our goal, the goal was to mention this equation for vector magnetic potential into as simple form as possible, so that it becomes easier for us to calculate the value of vector potential if we need it anywhere. So what he's doing here is that he's, instead of doing the calculations on vector magnetic potential again, he is referring to the calculations that we did back in electric scalar potential. So he's saying that the Poisson equation for vector electric scalar potential was nebula square V is equals to minus rho V over epsilon. This was the equation that we studied. So what he's doing is he is comparing these two equations. If you see the left hand side of these two equations, you will see that these two things are pretty similar. So we can basically use the same convention that we did use back in electric scalar potential in order to simplify this equation too. So he's saying that in electrostatics, the Poisson equation was this, and its a solution for volumetric charge density rho V occupying a volume V dash was basically V is equals to 1 over 4 by epsilon and the integral of rho V dV over R dash. So this was the solution, or we can say that this equation led to the Poisson's equation of this thing. We calculated this while we were studying the electric scalar potential. So he's saying that what if we compare these two things and we try to get to the solution of this thing in just like we did back here. So what he's saying is that if we want to uh, compare these two things, what will be the solution of vector magnetic potential? He's saying that if you take a look at this equation right here, you can see that we have nebula square. So we have nebula square, we have missed a sign of minus. This was a minus sign here. Okay, so what we have minus sign The same thing, we have rho v. Here we have j instead of rho v, but here we have epsilon in the denominator, while as compared to that we have permeability in numerator. So what we'll do is that if we want to convert this thing into this thing just like this, what we'll do is that we'll write 4 pi as it is, but there was epsilon in the denominator, but now the permeability is in the numerator, so we'll write this in numerator mu, and then instead of rho v we have jv, so we can write it as jv divided by r hat and then dv. So we can say that if we compare these two equations, this will give us the value of vector magnetic potential. If we want to mention this in the form of x, y, and z components, we can say that ax is going to be mu over 4 pi and then volumetric integral and then jx and then dv dash divided by r hat. Similarly for ay, similarly for az, and for a generic vector a we can write this as mentioned here, or if we have uh, current density, surface current density instead of volumetric current density, then we can replace this equation by this. A hat is going to be mu over 4 pi. Now we have surface integral and we have js, we have ds divided by r hat. So we know that we can replace jv dv with js ds with I and dl. So we know this, we have talked about this too many times now. So we can convert this to volumetric current density, we can convert this to surface current density, we can convert this to line current density according to the requirement that is given by the author in any numerical. So this make things easier. Now by this equation, if we have the value of mu, if we have the value of volumetric current density, and we know the type of geometry, we can easily calculate the value of a. So so our goal is achieved. He's saying that by looking at this equation we can say that vector potential gives us another way to find the value of p due to current carrying conductors, apart from Biot-Savart law and Ampere's law. For a given current distribution, this can be used to find the value of B. How? We'll first calculate the value of A by using this equation. It will be easier for us to calculate this integral as compared to the integral that we did calculate in by Ampere's law. Because there were two things, there were h, there was dl, and we have to calculate the value of dl according to h, even though we didn't know the value of h itself. So what he's saying that in some cases it becomes easier for us to calculate the value of a and then calculate the value of b by using the value of a, just like we did back in electric potentials case, where E was equals to minus nabla V. So he's saying that what this thing is providing us is with another method to calculate the value of vector magnetic uh, to calculate the value of magnetic field intensity by calculating the value of magnetic flux density. So he's saying that for simpler cases or for symmetrical cases, Ampere's law is a great method to calculate the value of H, as we have witnessed in the last two examples that it was pretty easy for us to calculate. But he's saying that for more complex type things, like the one in which we had a dipole and we wanted to calculate the value of H at a point which is not on its axis. So the thing is that that case becomes a pretty more complex, and in order to calculate the value of b, if you take a look at it by searching for it on Google, you will see that in most of the methods the value of h is calculated by using vector magnetic potential, because first of all they calculated the value of vector magnetic potential, and then by taking the curl of that vector magnetic potential they calculated the value of B. You can cross verify it by googling that uh, expression, how he derived that expression for any point P. So he's saying that for simpler cases, Ampere's law is great, but for a little bit complex structures, we will move to this vector magnetic potential. Apart from that, he's saying that magnetic flux, basically phi, is if we want to know that what is the value of phi, we know that B is basically magnetic flux density, so it is Weber per meter square. But what if we want to calculate the value of phi itself, Weber itself? For that case, he says that basically if we want to calculate the value of phi, so we need to know the value of B, and we need to know the amount of area for which we are calculating the phi. So phi is basically number of lines, but when we talk about magnetic flux density, we talk about number of lines crossing a particular area. So he's saying that if we want to calculate the value of phi, we know that we have to calculate B dot ds for that surface. Once we have this value, we will know that what are the number of lines at that particular area. So what he's saying is that if we change this expression by putting in the value of magnetic flux density in terms of vector magnetic potential, we can say that we will replace this P by nebula cross A, and that is dot ds. If you take a look at this expression, you will remember that this expression is pretty much similar pretty much similar to the left hand side of the Stokes theorem. This means that we can convert this type of integral into a more simpler integral in which there was a closed contour, and we could easily calculate the value of a dot dl for that contour. This will be equals to the phi. So if we want to calculate the value of phi and we have the value of B, we can use this expression. But if we want to calculate the value of phi by using vector magnetic potential, it will be easy for us to calculate the value by using this expression, by using a dot dl instead of b dot ds, because we know that surface integral is going to be a little bit more complicated as compared to line integral. So the what will be the value of contour, what will be the contour at which we are going to integrate this on? That contour is going to be a path which is binding the surface S. Which surface S? This surface S, the surface at which you are calculating the value of phi. So these are the applications. You can use the vector magnetic potential to find the value of phi. You can use the expression of vector magnetic potential to calculate the value of a magnetic flux density B itself, or you can use the value of vector magnetic potential to calculate self-inductance and mutual inductance and things like that. We will study that when we'll talk about inductance and capacitance, when we'll talk about inductance and mutual and self-inductance too. So these are basically the applications of vector magnetic potential. The next thing in our agenda is to talk about magnetic properties. We'll talk about magnetic properties of materials in the next lecture, but just to give you an introduction, if you reflect back to the last chapter in which we studied the electrical properties of material, what we did was we tried to understand how a material behaves under the influence of any external magnetic field, or whenever an external magnetic field was applied, how that material responded to it. And according to the response of that material, we classified that material into different categories. Like we said that this material is a conductor, we said that this material is a dielectric, we said that this conductor is a semiconductor, or this material is a semiconductor. So that was basically the thing on which our classification relied on, the thing was the electrical properties of that material. So the counterpart to that thing in magnetostatics is going to be the magnetic properties of the material. So we need to understand that why a material behaves in a certain way when it is exposed to the magnetic field or exposed to any external magnetic field, just like we studied how a dielectric behaves when it is placed in the vicinity of an external electric field, or how the conductor behaves when it is placed in the vicinity of any external electric field. We talked about it. We talked about the free electrons, we talked about the depletion region, we talked about all those things in order to understand why a material is basically acting in a certain way. Similarly, in order to understand why a material is showing a certain type of behavior whenever it is placed under the vicinity of an external magnetic field, we need to understand what is what is the basic principle that is making that material to act in that certain way. So in order to understand that, we need to understand what is happening inside that material, what is the thing that is related to, or the thing that basically the tiny little thing that responds to the external magnetic field, just like an electron responded to an external electric field by displacing, by changing its location. Whenever there was an external electric field, the electron changed its position and started to flow from lower potential to higher potential, if we're talking about conventional current. So just like that, uh, we have to understand what is happening inside a material once it is placed in the vicinity of an external magnetic field. We'll talk about that in the next lecture. That lecture is going to be a little bit more generic as compared to this. There won't be a lot of equations in that. So yeah, there's that. This is it for today. If you have any confusion about anything, you are welcome to ask your queries in the interactive session. Thank you so much.